Hey, good morning, chemistry team. It's your chemistry coach coming at you with video number 7 in our solids and solubility series. We're getting to the end here. How many ways can we screw up a solid solubility or dissolve that baby? A lot of different ways we could do it. So this is going to be part 2 in how we can increase a solid solubility. So in the last video, we looked at the salt effect. We looked at adding a ligand or whatever to pull that ion that's in equilibrium with the solid out of solution. This time we're going to look at those ions. Remember, the solid's in equilibrium with the cation and anion in solution. There's not a lot of cations and anions in solution, but they are there nonetheless. And we can attack them and take them out. We do anything. We put anything in that equilibrium system to reduce the concentrations of either the cation or anion on the right-hand side of the arrow. Le Chatelier's principle says you decrease those, boom, shifts to the right, solid solubility increases, and if we keep adding it, we could eventually dissolve the entire solid. Ho ho! So, this is what we're going to do on this one is, hey, what if the anion of the solid is a base, right? Whether it's like the hydroxide ion, magnesium hydroxide, calcium hydroxide, pretty common anion in solids, or even one that doesn't really look like one. It's a weak base, right? So if you look at your acid-base chart, do I have the acid-base chart here somewhere? I hope so. So if you look at what I handed here, the acid-base table, right? If you look at all of these, anything below water, right? All these weak bases, these ions, this is not a complete list. Any of these anions right here, they're below water, so they're stronger than water. They're going to ionize in water. And then you got the strong bases down here, right? Any of those will qualify as having weakly basic characters. So sulfide salts, fluoride salts, carbonates, I mean, you name it. There's a lot of options there. And if that has weakly basic character, I can add an acid represented as the hydronium ion, and that's going to neutralize it, and that's going to drop the concentration of that anion, which is going to shift this equilibrium to the right-hand side, increasing the solubility. That's the net result. So that's another way to increase solubility of a solid. Yay! Let's look at a couple of qualitative examples here. One kind of simplistically with Le Chatelier's principle. One of them where we're going to combine the two equations together and get an overall equation and overall K value. And then we'll look at some stuff mathematically, which may be in another video, maybe in this video. I'm not quite sure yet. Depends how much I go off on little rabbit trails. All right, let's walk through this together, or ideally do it before I do it. Let's say we have this solid right here. What's that? Copper 2 arsenate, something like that. Doesn't necessarily look acidic. I mean, look basic, but let's have a look. What are the ions in equilibrium with the solid? Let's draw the cation, let's draw the anion. So we've got a subscript of 3 here, so it's going to give us 3 of these copper ions. And the arsenate's a -3, just like the phosphate. If you look on the periodic table, the arsenic atom's right below the phosphorus, correct? And so if you got phosphate and arsenate, they're probably going to be the same charge. Even if you don't know it, that's a pretty valid guess. So if this is 3 minus, that would be a +2. So this is going to be an equilibrium. Whoops, I forgot my coefficient. 3 of the copper 2 ions. And then the subscript on the arsenate ion is 2. So that comes over and gives us 2 of the arsenates. Hey! Now, obviously, the copper ion is not going to have any kind of basic character. But in the last video, we talked about possibly complexing that out with a ligand or whatever. Let's look at this arsenate ion. A couple ways you can do it, right? You can look in here and go, hey, arsenic acid. Do you see arsenic acid? That's a weak acid, which means the conjugate base of that acid is itself a weak base. So this is weakly basic. Identifying that, right? Now remember, if it's an anion from a strong acid like chloride or iodide or something like that, or nitrate, those are neutral. So that wouldn't work. They would be unimpacted by adding any acid. But if I add an acid to this puppy, it's going bye-bye, isn't it? So if we add acid, now whether it doesn't matter what the acid is, let's just generically do it as the hydronium ion. Right? Let's say we add that acid. Boom. It's going to attack that, isn't it? It's going to donate its hydrogen ions, and you get the ASO42 minus, then you could keep going, go H2, ASO4 minus, etc., etc. So as acid, it reacts with that arsenate ion. Right? That decreases it. Le Chatelet's principle. That's going to cause that to drop. So the concentration of this decreases. And the equilibrium shifts to the right. Kind of what we said before. So we're going to the right. So this is going to drop. This will shift to the right. And that will, so the solid's going to continually, as long as we keep adding acid to it, dropping that arsenate ion, the solid will continue to dissolve, replenishing. It goes red alert, we were in equilibrium. The arsenate ion has decreased somehow. The equilibrium system doesn't care how. It just knows we were happy. We were in equilibrium with constant concentrations of all our cations and anions. And boom, all of a sudden, that one's low. So it goes red alert, dissolve more to replenish the lost anions. And it'll keep dissolving more as long as we keep adding acid, up to the point where you either run out of acid that you're adding or run out of solid to replenish it, and solid goes goodbye, right? You can increase the solubility or completely dissolve it. You have to run some quantitative math on that, right? So the net effect is solid. This increases the solid solubility, possibly even dissolving it. So let's do a qualitative one, sort of, where we take the two equations, add them together, manipulate it. You know, the overall K is K1 times K2. You know, review that video if you need to, manipulating equilibrium equations. And we'll see what the overall K value is. And if it's really big, that means it's product dominant. If it's bigger than 10 to the 10, it probably dissolves the solid. If it's less, smaller than 1, right? Remember, K bigger than 1 is product dominant. K less than 1 is reactant dominant. So if it's less than 1, it may increase the solubility a little bit, but it probably wouldn't dissolve it per se. So let's do that. And then if we have time, we'll do a quantitative one in this video. If not, I'll make a whole separate video on like pH effects, how we can control solid solubilities, or whether a solid even forms or keep it from dissolving by controlling the pH. Oh. All right, let's see if you can do this one on your own. This is all review, right? There's nothing really new here. It's just we're introducing solid equilibria. So how will adding nitric acid, right? You got to know, is that a weak or strong acid? Adding nitric acid solution to this solid, how will it impact its solubility? Now, really, you could say it increases it, duh. But what I want to do now is get the individual equilibria equations, add them together, and get an overall K value. I probably would state that on a quiz or test to make it a little more obvious what I'm asking for. That may be a weird-looking solid. You're like, what's that? So the N3 minus the triad, it's got 3 nitrogen atoms combined together in a polyatomic ion with a -1 charge. You may not have seen that before. It's called azide. So this is lead 2 azide, because that's a -1 charge. There's 2 of them, so this is a lead 2 azide. Pretty crazy stuff, man. There's a lot of weird ones out there. So let's take a look at what ions are present in the equilibrium with the solid, and let's look at what ions we're adding through the nitric acid. And we go through the thinking, do we have common ion? Do we have any reactions going on? And that will give us our second equation. So let's always start, if you're unsure what to do, always start with the equilibrium of a solid. So let's bring that down. Let's call this equation 1. Okay? So let's draw that solid. So I got my lead 2 azide. Weird stuff. Hopefully we can find that on the KSP table. If not, I'll have to stop this and do a whole new video. All right, so that's going to be in equilibrium with the lead 2 ion. And I have one of them, right? There's a subscript of 1 here, but there's a subscript of 2 on the azide. So I have 2 of the azide ions. Now let's look at the K values. So K1, this is a solid dissolving, so that's KSP. So K1 will be equal to, that's an ugly looking K. Imagine that looks like a capital K. So it's just KSP, right? It's not backwards, it's forwards. Right? We may need to manipulate it if we're going to add things together. So we may need to square that or something like that in the future. But let's take a look. Now, what are we adding? This is having a great time, perfectly existing on its own, happy, happy state. The lead-2 ion, the azide ions have a constant concentration. We could easily calculate that using an ice table, solving for x. Right? This would be x, 2x. But now we're jacking something into the system. This is Le Chatelier's principle at its finest. Squirt in some nitric acid. Concentration doesn't really matter at this point. We're just squirting some nitric acid in. Understanding this is a strong acid. All right, so that HNO3 exists as the hydronium ion and the nitrate ion. Correct? 100%. Right? That's one of the 6 strong acids that we teach you. HCl, HBr, HI, HClO4, H2SO4, HNO3. Memorize those! That will help your life tremendously. Knowing whether an acid's strong or weak. Now we have 4 possible combinations. Let's take a look. Are either of these in common? I always look for the common ion first. No, there's no hydronium ion in the equilibrium system. There's no nitrate ion in the equilibrium system, so there's no common ion. If there was, it would increase the common ion and shift left and decrease the solubility. Well, that's not happening in this case. That was in a different video a couple videos ago. Can there be a reaction now? And if there's no reaction, this would just be a salt effect, right? So boom, off it would go to the right a little bit. Well, could the hydronium ion react with the lead-2 ion? Probably not. They're both cations. So I'm going to eliminate that as an option. Could the nitrate ion react with the azide ion? Well, they're both anions. Probably not. Right? They're probably more likely going to repel each other. So there's 4 combinations. You can kill cation, cation, anion, anion. Gone. Now let's go diagonally. Could the lead-2 ion react with a nitrate ion? You have to look at possible complex ion formation. Is the nitrate ion a ligand that could react with the lead? We'd have to probably have at least 4 molar or higher of the nitric acid. And since I didn't give you the concentration, see, if I put like 4, 5, 6 molar on there, that's a big hint that you're probably going to get a complex ion like we did in the last video. But nitrate doesn't form. You'll see it doesn't act as a ligand. So we're not going to get any complex ion. We also have to look and see, could we get another solid, say a secondary solid? Well, nitrates don't form solids. All right. So the lead and the nitrate, nothing's going to happen. No solid formation, no complex ion formation. Now let's take a look at the hydronium ion. With the azide ion. Understanding that this is a weak base, right? And the hydronium comes from a strong acid. Neutralization reaction, my friends. So what's going to happen is that azide is going to come down in equation 2. So let's write that azide ion. That's going to react with the hydronium ion from the strong acid, right? So that's in equilibrium with the solid. This is what we added to it. The nitrate does diddly jack squat. Boom, we get a neutralization. So always look common ion first. That's by far the most dominant. Then look for reactions. That's the next most dominant if you don't have common ion. And then last but not least, do the salt effect. If nothing happens, do the salt effect. Because the salt effect's really minor compared to the common ion effect and compared to any kind of neutralization reactions or complex ion formation, right? That will always dominate over the salt effect. So only worry about the salt effect if nothing else is going on, all right? This is going to donate its H+. Oh, fumble! I rolled a 1. Boom. So that H+ comes over. So we're going to get HN3. That's a -1, so it just picks up 1 hydrogen. Give us a monoprotic acid, HN3 aqueous. What's that? Look on your Ka table. All right, and then this becomes water. Whoa, that's an ugly O. There we go. So that's our second. We got 2 equilibriums. Can you sense we're going to add these together? Pause the video. Put a big line here. Add these together. Make sure you remove the like species. That when you add them together, the azide ion has to go bye-bye. Bye-bye. So you got to multiply this by 2. Find what the K value is of that. Good luck. And you got to square it. And see if you can calculate an overall K for me. This goes back to chapter 15. One of the first things we looked at in chapter 15 equilibrium was doing this. Have at it. All right. So what is this K value? Let's look at K2. What is K2? Let's think about the possibilities. You only got a few things. Weak acids, you got KAs, KBs, KWs, KSPs, and KFs. Well, there's no solid in there, so it's not a KSP. Would you agree? There's no complex ion in there, so there's no KF. So we can wipe out KF or KSP. There's no OH minus in there, so it can't be a KB because that's forming. It's a KB is a base reacting with water to form OH minus and something else, right? I don't see two waters reacting together, so it's not a KW. This has to be a Ka, but it's backwards. It's a weak acid reacting with water to form the hydronium ion in the conjugate base. So this is the inverse of the Ka value for HN3. Oh, let's see if we can find an HN3 on our Ka table. Ho, ho, ho. Here's our Ka table. Let's see. Do you see it? Hydrozoic acid right there. What a bing, what a boom with a Ka of 1.9 times 10 to minus 5. There it is. So this is going to be the inverse of that. Since it's backwards, it's going to be 1 over that. Get that dust out of your brain, my friends. All right, squirt some WD-40 in there, work the rust out. But this only has one azide ion. That has two. So I have to take this entire equation. Dun, 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 dun. Would you agree? I have to multiply this by 2. That would give me 2 azides here, which will cancel out the 2 azides there. So therefore, if I multiply that by 2, I have to square the K value. Remember? Chemists manipulate equations and mess everything up. So let's add these together. Let's get our overall equation. You ready? So we're going to have the lead 2 azide solid plus 2N3 minus, which will cancel out, plus 2. Remember, we multiply everything in there by 2. So we're going to get the solid plus 2 hydroniums, because the azide is going to cancel out, giving us the lead 2 ion. Those 2 azides will cancel out, plus 2 of the weak acid there, hydrozoic acid, plus 2 waters. That'll be our overall equation. And then we just multiply the K1 times the K2, right, to get the overall K. So here we go. So this will be the lead 2 azide solid. Nothing else here. That goes away, right? That's going to go and cancel that. So I get the 2 hydronium ions. So effectively, we're adding acid to the solid, right? Just via Hess's law. We're going to get the lead 2 ion. The azide goes away. We're going to get 2 times the hydrozoic acid. I keep wanting to go NH3. This is a mind bender. It's HN3, not NH3. It's not ammonia. That can get really confusing. Who invented that acid? Darn them. And we're going to get 2 times that, or 2. I'm writing smaller and smaller. Squish! Squishy! I have a funny feeling I'm going to have to do the pH effects on a separate video because I'm having fun with this. I love this stuff. It's so logical. All right. I want you to tell me, right? I'm going to have to obviously erase this board. What is the overall K value for that? So you're going to take K1 times K2, which will be the KSP of the lead 2 azide. Look it up on your KSP table. Times the inverse of the Ka value for hydrozoic acid squared. Do it. Let me erase my board. All right, I haven't done it yet. What I did is I made some room, right? I rewrote the overall equation up there. So we know that K overall will be K1 times K2, right? And again, K1 was the KSP for the lead 2 azide solid. K2 was 1 over the Ka value squared for the hydrozoic acid. So we got to look up the KSP. I'll tell you the truth here. Well, I always tell you the truth. My eyes are going bad. They've been going bad since 9th grade when I was like, I can't see the board anymore, but I didn't want to tell anybody, you know what I mean? So, I don't know, late middle school, early high school, you don't want to get ridiculed and things like that. I don't want to have to wear glasses, so I didn't tell anybody. But yeah, it is what it is, right? But I always, and even today, so I look at some of these tables, and a lot of times I can't see the number. Is that a -7 or a -9? Is that a 3 or an 8? So a lot of times I'll write down the wrong number, or I'll look at the one right. I lose. I should get a ruler or the side of a piece of paper, because if I'm looking across on this darn thing, right? A lot of times I'll look for something and I go, here it is, right there. And I go to the wrong one. I'm like, and you get the test back. You're like, I knew what I was doing. And I wrote the stupid wrong number down there. Not a big deal. You lose a few points in calories. In the real world, you just killed somebody, right? So you better make sure you do it right in the real world, doing surgery or building a bridge or something. Oop, off by factor 2. The bridge fell down. All the cars tumble. It's just bad. You can't screw up like that in the real world. So let's look up the KSP value for the lead 2 azide. I have no idea where that is. And again, I'm looking at a mirror image upside down and I don't have my glasses on. There's it. Okay, so do you see the lead? You guys tell me if I'm doing the right number, right? They'll email me if I'm screwing it up. There's that weird looking formula. Is that 2.5 times 10 to the minus, is that a 9? Yep, 2.5 times 10 minus 9. You guys see it right there? 2.5 times 10 minus 9. So let's write that down. 2.5. And I'm not squaring that. I'm not inversing it. It's just a straight up KSP. All right? Let's make that a little more obvious. 2.5 times 10 minus 9. Now let's find the Ka value for HN3. What was that, hydrozoic acid or some weird thing like that? All right, so here's our K values. Hydrozoic acid, HN3, looks like a 1.9 times 10 to minus 5. You see that? 1.9 times 10 to minus 5. Let's write that there. Don't forget to square it. A lot of times I'll screw that up too. I'll forget to square things. So it's going to be that, effectively divided by that twice, right? Two significant digits. I get 6.9. Vertical dash line 2.5. It's closer to 6.9 than 7.0, so I'm going to keep that as 6.9. That is your overall K value for that equation. So, yeah, it's bigger than 1, right? Barely, right? Which means it's going to be slightly product favored, but it's not even close to 10 to the 10th. So I wouldn't say that the solid dissolves completely, but I would definitely say this is slightly product dominant. Let's do this in green. So I'll say it's slightly product favored. So the solubility of the solid, let's write that solid in there, increases, right? And you could have just said that with the Le Chatelier's principle, right? The hydronium is going to react with the azide ion, drops it, shifts right to compensate for it, okay? Until you're out of acid. But this kind of shows you how you can play with that. This is kind of a transition between a really hard quantitative problem and a real simple qualitative problem like Le Chatelier's principle. So I talked on and on that one. We'll do one more video and end this chapter, and we'll look at using buffers and controlling the pH of solutions to control solids and precipitates. So like I said, we could prevent precipitates from forming, or we could cause one to form by adjusting the pH, by controlling, usually it's the hydroxide ion concentration. But yeah, we have control with buffers. It's going to be pretty cool. That's the end of this one. Enjoy.